Good morning everyone. My name is Mrudula, working as Assistant Professor in the Department of Electrical and Electronics Engineering at MLR Institute of Technology, Hyderabad. Today I am going to discuss a topic about selecting and sizing of components in electrical systems. Here we will discuss about things to be considered while selecting and sizing of components, the technical parameters and non-technical parameters, and earthing in commercial installation systems. First one, things to be considered while selecting and sizing of the components. Parameters for component selection. For selecting a different type of components, first we need to know the parameters of that. The parameters to be considered for selecting can be broadly classified into technical as well as non-technical parameters. So the parameters are divided into technical and non-technical parameters. The selection process is many a time a fine balancing act between technical and non-technical aspects. There should be a balance between technical and non-technical aspects. The subsequent sections upon these parameters we will be seeing here. Like these are the different technical parameters that should be considered. While describing, you can see here the first one is functionality. The first and the foremost question to be asked by the designer is whether the component under consideration meets all the functions desired by the application. Based on the application, all the needs are being attained or not. An example could be whether a certain power supply IC meets the voltage or current requirements of an application. That means for a particular load, for a particular application, whether it is meeting the voltage or current requirements or not. Based on that, the power supply, how much of power supply should be taken is being decided. The second one is DC electrical characteristics. The most important DC electrical characteristics of a device to be considered is supply voltage. The most important thing is supply voltage at which the device operates. In systems with multiple supply voltages. It is important to check the device input-output voltage tolerance. It is important to check the input and output voltage tolerance level to decide whether the voltage translator are needed between. That means the voltage levels should be adjusted or not. So to decide that the translator are needed or not between the various components. The logic levels. You can see the logic levels of input and output lines decide how the components fits into the overall system. Okay, so this is DC electrical characteristics. Next one is AC electrical characteristics. The most important AC electrical characteristics to be considered are frequency of operation. The rise time, fall time, propagation delay, and setup and hold times. So for AC component, for DC component, the voltage or the current will be stable. So all these factors will not be considered. But in AC electrical characteristics, we need to consider the rise time. Like this will be your voltage supply, there will be no fluctuations, but in AC you will be having like this. So the voltage rise time, this time is your rise time, this time is your fall time, this is your you can see the AC. For this AC, from here to here, from this point to this time, you will call it as rise time. From here to here, you will call it as fall time. Okay, if at all any delay is there, so this particular thing you will call it as delay time. Okay, so rise time, fall time, propagation delay, setup and hold times, all these to be considered in AC. It is important to consider the minimum value, maximum value of these parameters also. This is your maximum value, this is your minimum value. So the maximum value and minimum value also to be considered. Okay, so here in the AC components, we need to consider the rise time, fall time, propagation delay, setup, hold times, minimum and maximum values. Next one is power consumption. In general, these power consumption, it is used to be low as possible. Mostly we will try to choose a component which is consuming less amount of energy. This becomes, in order to save the energy, we will try to use a component which is consuming less amount of energy. So this becomes a decisive factor. This becomes a decisive factor in choosing the components for portable battery operation systems. Means the components which we are using, we need to check whether they are portable, that is small in size, more efficient and consumes less amount of energy. So always we will prefer this type of component. So the designer could look at a specific feature such as availability of sleep modes, idle modes, etc. also. They will check for this also. This will enable the reduce, it will enable to reduce the power consumption when the device is not active. That means when the device is in active mode, it will consume the energy. When the device is in off stage, it should not consume any kind of energy. Next, supporting circuit elements. For every electronic good, there will be some kind of supporting elements for that, supporting circuit for that. While choosing a component, it is essential to consider the additional circuitry. It is essential to consider the additional circuitry that allows the components to operate, with the levels of integration going ever higher. It would be better to choose the components that support greater on chip features, so that the number of electrical components are being reduced. Means with less number of components, we need to complete the task, so that the consumption is also less, the overall cost is also less. So always we will prefer to have reduced number of components. Greater the on-chip features, lesser the cost, physical size, and power consumption. So always we will choose a particular device which is portable, that is small in size, which is less in cost, which will which will consume very less amount of energy, and which requires very less number of additional supporting circuits for that. So based on this, we will decide the component. Next, operating environmental requirements. Like every component is specified to operate at a certain temperature. So every component is designed to operate at a certain temperature and relative humidity also. So the component has relative humidity as well as certain bearable temperature also for that. So based on this criteria, components are classified as belonging to commercial grade. They are classified into commercial grade. Second one is industrial grade, and third one is military grade. So the components are being classified into commercial grade, industrial grade, and military grade based on the relative humidity. Like the component should be placed at different places. So at that particular place, we should first decide its humidity and its temperature. Based on that, we will decide which kind of components is applicable for that particular application. So the designer could choose the appropriate grade component based on the system's operating environment. Next one is regulatory requirements. Regulatory requirements for different national regulatory bodies. Place constraints on choice of components. Another example to verify whether the module or the subassembly like AC to DC converter is being considered is certified to meet the FFC and UL requirements. So first we need to check whether the module is applicable or not, and next we need to check whether it is certified whether it is certified by different things like FCC, CE and UL also. So we need to check for the certifications also. Next one is reliability data. Comparison of component reliability parameters such as mean time between the failures. So the component may sometimes fail, so we need to decide the mean time between the failure of different components that is being considered would be essential for design of high reliability systems, Next one is IP availability. When the component under consideration is a processor or a programmable logic device, that is PLC, programmable logic device. So when the component under consideration is a processor or a PLC such as CPLD and FPGA, availability of intellectual property IP. So that is to be licensed from the IC vendor and the third parties. From a vendor and as well as from the third parties, it should be licensed before selecting that particular device and before releasing into the market also. So these are some of the technical terms, and now we are going to discuss about the non-technical terms or non-technical parameters that should be considered. First one is cost. Non-technical parameter, first one is cost. Cost is a critical constraint of any electrical selection. That is, for selecting any kind of component for any kind of application, first and foremost, we would like to check about the cost of the component. So, the important point to be considered is the cost of total solution, just the cost of particular component under consideration. Okay, so we need to consider the cost. Second one is multiple sources. Second one is multiple sources. For mass production, having multiple suppliers, if we are having multiple suppliers and manufacturers for a component, is desirable feature since it easier procurement and lowest cost can be competition due to competition. Next one is stage of production. It is essential to consider the stage of production of the component. That is, it is in the starting stage or in the ending stage. So, based on the stage of production. Next one is legacy. Components used in the previous version of the system are good candidates for new version of the system. So, this permits use of a device or a software or a layout and knowledge, thereby reducing the risk. So, instead of using a new component, it is better to use the new version of the older component, so which reduces the risk. And while reusing the legacy like old components, it is important to verify whether the component is still in active production, whether it is working properly or not. We need to check it once and then we need to use that component. And also, if there is any known issue with the component, we need to check if there is any issue under active motion, if it is active or not. So, earthing in commercial installation system. Earthing in a commercial installation involves connecting an electrical system to the earthing system or electrode. Connecting an electrical system to an earthing system or electrode to ensure the safety. During the faulty conditions, mostly we will connect this. So, in order to avoid the fault conditions, in order to avoid the shock, we will mostly provide this earthing system. So, this provides a path for electrical circuit to flow through the ground if any case of fault or overload occurs. Like if any fault or overload occurs, in order to reduce the risk, in order to reduce the shock or damage, we will be using this earthing system where the electrical current flows through the ground. So, here are some of the steps of installing earthing. That is, the first step is select the type and location of the earthing system. There are different types of earthing system, as I said in the previous session. That is pipe earthing, strip earthing, plate earthing. So, based on the cost and based on the load which is being connected to that, so based on that, we will be choosing different types of earthing systems. So, first of all, we need to select the type and location where to place this earthing system. We need to choose the location first. In order to choose the earthing system, there should not be any obstacles near to this earthing system, and the minimum of 5 to 10 meters of gap should be there between the earthing system and the building. So, the second point is prepare the ground first. Prepare the ground first means first we need to check the soil whether the soil is like a sand or like having rocks, more number of rocks, or it is a wet land. So based on whether what is the resistance of the soil. So based on all these criteria, so based on the type of the soil, we need to decide which type of grounding is being placed. So we need to we need to first dig the ground, we need to check the soil resistance, and we need to check whether the soil is having more number of rocks, it is sandy, or like it is a wet ground and all. Next, third one is install an electrode. Install the electrode. So in a pipe type of earthing, we will be placing a pipe, and in a strip type of earthing, we will be placing a strip or an electrode. So we need to install the electrode after digging the ground. Next, backfill the hole. So after digging the ground, we will be placing the electrode with minimum 3 to 5 meters depth, and after placing the electrode, proper filling should be, means the proper in different types of groundings. In some type of groundings we will be filling with salt, and in some type of grounding we will be filling with sand or coal. So the filling should be done properly. Next one is connect the electrode. We should, after filling the electrode with sand or salt or coal, the electrode should be connected to the different circuit system. Okay. Next one is choose the conductor. Which type of material to be connected? First we should choose the conductor and then run the conductor. So these are the different steps which are used for installation of an earthing system, which can be any kind of earthing system. So the same process is being followed for different types of earthing system, which is mainly used for safety purpose if at all any fault occurs. These are the different types of earthing systems, that is plate earthing, pipe earthing, rod earthing and strip earthing. First one, plate earthing. A metal plate. A metal plate is used, mostly made up of copper or galvanized iron, which is being buried inside the ground and connected to an electrical system. This is commonly used in small commercial and residential buildings. It is mostly used in small commercial and residential buildings. That means we need to dig the sand on the earth and we need to place this plate made up of copper or galvanized iron, that we need to place below 3 meters of depth, and after that we need to fill the remaining with sand or salt. Next one is pipe earthing. Here in this, a metal pipe such as which is again made up of copper or galvanized iron is driven vertically. Previously, if this is the ground level, and this height is around 3 meters. Below that we have placed a plate for plate earthing. Now instead of placing a plate, we will be placing a pipe. And we will be placing a pipe made up of galvanized iron or copper wire. It is vertically into the ground and connected to the electrical system. This is suitable for high soil resistivity. Means the plate earthing is used for, this is used for low resistive soil. This is used for low resistive soil and this is used for high resistive soil. Next one is rod earthing. That means instead of this pipe, we will be placing a rod. We will be placing a rod. So the rod, metal rod, usually made up of again the copper or galvanized iron, is being placed vertically into the ground and connected to the electrical system, and this is also used for low soil resistivity. So for low soil resistivity, we can use plate earthing as well as rod earthing both. And for high resistance, we will be using pipe earthing. The last one is strip earthing. The last one is strip earthing. Instead of rod, now we will be using a strip. We will be using a strip. The strip will be around, this will be around 38 mm and the width will be around 12 mm, 12 or 3 mm, sorry. It will be around 3 mm and this is around 3 meters below. So this strip is again made up of copper or galvanized iron, which is buried horizontally in a trench and connected to an electrical system. This is commonly used in industrial and commercial settings. So this is mostly used in industrial and commercial settings. So here you can see different types of earthings, that is plate earthing, pipe earthing, rod earthing and strip earthing. In next topic, I would like to discuss about the different illumination systems. Thank you.